This time we'll be looking at graphical representation of simple harmonic motion. We have looked at simple harmonic motion in the perspective of a swinging pendulum. We have also looked at it in the perspective of mass-loaded vertical spring. And we want to look at it as simple harmonic motion in the graphical representation. What do you mean by graphical representation? You know, when we're talking about simple harmonic motion, in the case of simple pendulum, we describe terms like periods, the time taken for one complete circle or oscillation. So many students are always confused. We're talking about a swinging pendulum. Maybe this is A, B, C. This is assumed to be the equilibrium position or the rest position. By the time you displace it and release it, keep on going to and fro. So the journey from A through B to C is half a circle, and the journey from C through B to A is another half a circle. So we're talking about oscillation or one complete oscillation as a circle. So graphically, when you look at this, this is the X, Y position, is a graphical representation. And most of the times, we'll talk about the origin. This is the Y, this is the X axis. So, if we are talking about the swinging pendulum, by the time it is in its equilibrium position, this is assumed to be the origin. By the time you displace and release and it is swinging, it is performing this type of. So this is what we mean by the graphical representation. By the time it's assuming the journey starts from point A and move to C, it has covered this distance. That is half a circle. By the time it moves from point C through B to A, it has covered another half a circle. And when you look at this diagram, we have pi, 2 pi, 3 pi, 4 pi. So pi means, in terms of degree, pi means 180 degrees. That is half a circle. 2 pi, we're talking about 360 degrees, and so on. So our point of interest here is we are looking at simple harmonic motion in a graphical point of view. So this is the rest position. By the time you displace, it will swing. I will have this. The question is, well, we normally talk about sine wave and cosine wave form. These are two concepts that students always get confused with easily. Sine wave start from the origin. This is sine wave form. Then cosine wave, on the other hand, does not start from the origin. The reason is, this is the origin, this is the point maybe 1. Sine 0, remember, sine 0 is 0. Sine 0, the rest position, sine 0 is 0. And that's the reason why for a sine waveform, it normally starts from the origin. Sine 0 is 0. Then cos 0 is 1. And that's the reason why for cosine waveform does not start from the origin. So looking at this, we have 3 diagrams here, A, B, and C. This is the displacement, this is the velocity, this is the acceleration. So our interest here will be how we look at the displacements. And we know that displacements x is given as A sine theta, where A is the amplitude. We have defined what is amplitude. Remember, when we're talking about simple harmonic motion, we mention angular displacement as theta all over t. And if you make theta the subject, theta becomes omega t. So we can write this expression as x equal to A sine omega t. Let's assume this is equation 1. Is that right? That is equation 1. Then we now talk about the velocity. We know that velocity is displacement over time. So by the time equation 1 represents the displacement, then velocity is equal to displacement, that is the x all over the t. So by the time we differentiate equation 1, we can put this v is equal to the x, the t. We are differentiating with respect to t. So if you differentiate sine, we get cos. And remember, when you differentiate omega t, you get omega. So it will be omega A cos omega t. And that would be our equation 2. So this is the velocity. This is the velocity. So if you want to, we'll play around with this. We'll play around with equation 2. Recall that sine square theta plus cos square theta is equal to 1. In trigonometry, this is an identity. So by the time you make, but what we have here is cos theta. But in line with what we are discussing, we can write this as sine square omega t plus cos square omega t equal to 1. So if you make cos square omega t the subject, cos square omega t equal to, taking sine square omega t to the other side become minus. So this will be 1 minus sine square omega t. Is that right? So if this equation 3, if you now substitute equation 3 into 2, substitute equation 3 into equation 2, it becomes v equal to, we have omega a, but what we have here is cos. So by the time you make cos omega t the subject, becomes square root of this. So we'll now substitute this as square root of 1 minus sine square omega t. So we need to play around with this. We need to play around with this. Remember, we said earlier that x is equal to a sine omega t. We still come back to this. So have this in mind. So if you now square both sides, we have v square equal to omega a square root of 1 minus sine square omega t, as we are squaring both sides. So by the time you evaluate this, you have v square equal to omega square a square 1 minus sine square omega t. And then we can write this. If you evaluate this, we have v that will be equal to the plus or minus square root of, if you do the square root of omega square, you have omega square, that is omega square will become omega square root of a minus, that is a square minus a square sine square omega t. Yes. And then remember, we have recall. That is what I was drawing your attention. Recall that x is equal to a, that is the displacement, times omega t. By the time you substitute this equation here, we have v to be equal to plus or minus omega square root of a squared minus x squared. We substitute that here, we'll have this. And this is the velocity. And this is the velocity. So when we are talking about acceleration, we are talking about acceleration. By the time, remember, recall, we said that velocity was a omega cos omega t. You can remember this equation. So this is velocity. So by the time you want to get acceleration a, acceleration becomes the v, the t. If you differentiate this equation v, which is, that is v is equal to a omega cos omega t. Remember, you are differentiating with respect to t. And by the time you differentiate cos, you are going to get minus. This is what we are differentiating. So omega. So acceleration now becomes a omega square, because if you differentiate omega t, you have omega. So this becomes omega square. This, remember, this is minus sine omega t. Is that right? And what is a sine omega t? Is x. So we can write this as E equal to minus, remember, okay, let's put it this way, recall that x is equal to A sine omega t. So we can write this, therefore, acceleration becomes minus omega square x, and this is the acceleration. We have defined displacement x as A sine omega t. We have defined velocity as omega, that is plus or minus square root, that is plus or minus omega square root of a square minus x square, and acceleration as minus a, acceleration as minus omega square x. So these are the important equations when you talk about representation of simple harmonic motion graphically. So we have a problem here. A pendulum bulb undergoing simple harmonic motion has a period of 0.4 seconds. It is released from a displacement of 1 cm from its rest position. Calculate the velocity of the bulb when it is 0.2 cm from its maximum displacement. So this is the formula you appeal to. V is equal to plus or minus omega square root of a square minus x square. So all these parameters are given. Remember, you have t is given as 0.4 seconds. Is that right? So with this, we can calculate omega. Omega is equal to 2 pi all over t. Is that right? Which you can evaluate because pi is a constant. 2 pi, that is 2 times 3.142 divided by 0.4. And that will give you your omega. Amplitude is given, displacement is also given. So you can substitute to get your velocity. Do it and let me